Okay, hello honor students. Before I start this video, just a quick note about it. I'm going to be proving here by using the mean value theorem and a new method of proof called proofs by contradiction that the natural log of 0.5 is less than 0. That's exactly the problem that I write out a proof for on your worksheet. So you don't need to watch this video. If you're comfortable just reading through that proof and it makes sense to you, that's going to give you all the information you need about how to use mean value theorem together with a proof by contradiction in order to answer the questions that follow. I'm creating this video because I recognize that sometimes reading a proof is a little bit harder than actually sort of talking through it with somebody. So you've got the option. But if you're comfortable reading the proof, or if you want to challenge yourself and just try reading the proof, totally fine. If you prefer to watch the video, that's fine. It's entirely up to you. Okay. So we're going to be doing this with what I call proof, what I don't call it, everybody calls it, what's called a proof by contradiction. Okay. Now proofs by contradiction are great for egomaniacs because egomaniacs assume they are never wrong. So that if they were wrong, the world would explode. So basically, here's how it works. I'm going to start by stating my claim. My claim is that the natural log of 0.5 is less than 0. Okay, I believe that is true, and I'm going to spend this time on this proof proving it. Okay. Then, my second line, I'm going to suppose not. So I'm going to suppose that I am wrong. Now, if I were an egomaniac, that would be impossible. I'm not really an egomaniac, but I'm going to show that that's not possible, that that's going to lead to a contradiction. Okay. Couple of things here. Super important. Your first line is going to be your claim. It must be identified as a claim. If you just write natural log of 0.5 is less than 0, you're assuming what you're trying to prove. That's like the number one rule not to violate in proofwriting. Don't assume what you're trying to prove. So it's okay to state, this is the thing I'm going to try to prove, but it must be identified as your claim. Okay. Second important thing, you gotta state it before you can suppose it's not true. Okay? Sometimes people will start a proof with suppose not, and it's sort of like, what am I supposing is not true? You've got to tell me what it is that I'm supposing is not true. So the claim is the statement that I believe is true. The suppose not, we're just pretending that it's not true. Okay, and then I'm going to spell out what does that mean. What that means is that the natural log of 0.5 would be bigger than or equal to 0. Notice if a strict inequality is not true, then the reverse inclusive inequality would have to be true. Okay, so at this point, this is when the mean value theorem is going to enter in. Because what I'm going to do is I'm going to use the natural log function because I know that that's continuous and differentiable. So on any closed interval within its domain, it's going to satisfy the hypotheses of the mean value theorem. I'm going to try to find an interval with 0.5 as one of the endpoints so that I can create a slope of a secant line, and this is going to then tell me something about the slope of that secant line. So I'm going to draw a picture over here. This is not a necessary part of the proof, but it kind of helps me in figuring things out and in visualizing what's going on. So if here's 0.5, okay, now we're supposing, although we don't really believe it, that the natural log of 0.5 is bigger than or equal to 0. I'm going to draw it as if it's bigger, but I'm going to remind myself that's just because when I draw a picture, I've got to put a point somewhere. I'm actually supposing that it's bigger than, which would be above the x-axis, or equal to. So it could be down here. Okay, so that would give me my point 0.5, ln of 0.5. Now I want to think about whether there's a number, an x value close to 0.5 that could be a good second endpoint for my interval. Okay, and I don't think I want to go to the left because that's taking me towards 0, which isn't in the domain. But if I go to the right, natural log of 1 is very simple because the natural log of 1 is just 0. And that's going to allow me to create this secant line. Now, if the natural log of 0.5 is bigger than 0, the slope of that secant line will be negative. If the natural log of 0.5 was equal to 0, the slope of that line would be 0. Okay. Okay, so let's write this out. Okay, so the natural log of x, let's call that f of x, the natural log of x is continuous on the closed interval from 0.5 to 1. It's continuous everywhere, but for the mean value theorem, I need it to be continuous on the closed interval with the two endpoints that I've chosen. Okay. F of x, which is the natural log of x, is differentiable on the open interval from 0.5 to 1. Now I know this particular function happens to be differentiable even at the endpoints, but I'm generally going to make it so that I have a perfect match for the hypotheses of the mean value theorem. So now I can say by the mean value theorem, there is an x value c in the interval from 0.5 to 1. The conclusion always puts the x value in the open interval, okay, such that f prime of c is equal to the slope of this line, which would be the natural log of 0.5 minus 0 over 0.5 minus 1. Oops, I'm sorry, f prime of c. Okay, excellent. So that is going to lead to my contradiction. So let's just explore this a little bit. Okay. If I look at the natural log of 0.5 minus 0 over 0.5 minus 1, that's going to be the natural log of 0.5 over negative 0.5. I'm just going to write that as negative 1/2, because then I can see that's negative 2 times the natural log of 0.5. Okay. And because we have supposed that this is bigger than or equal to 0, when I multiply it by a negative, that would make it less than or equal to 0. Okay. So we've established what we had sort of drawn over here, that the slope of that secant line will be either negative or 0. But I know that f prime of x, the derivative of the natural log function, is 1 over x. It's the reciprocal function. So f prime of c is 1 over c. But by the mean value theorem, that's supposed to be negative 2 natural log of 0.5, which we've just said is less than or equal to 0. Now, if 1 over c is less than or equal to 0, that would imply that c is, well, obviously it can't be equal to 0, but that would imply that c would have to be, I'll say, bleh. C obviously can't be 0 because it's in the denominator, okay? So that would imply that c is less than 0, okay? Because if the reciprocal of a number I can see can't be 0, so it must be negative. But if the reciprocal of a number is negative, then that number must be negative. But c was in the interval from 0.5 to 1. That's my contradiction. Okay. So this is the fun symbol to draw. That says we've reached a contradiction. You have these arrows sort of colliding. It's like, boom, the world has blown up. Okay. So when you reach a contradiction, that says, oh, why did we reach this contradiction? Well, way back when, we supposed that the claim that we actually believed was not true. And that's what led to this. So then we say, thus, the original claim that the natural log of 0.5 was less than 0 must be true. Okay. So reach your contradiction. Don't forget to then state your conclusion, that what you initially claimed before you supposed it wasn't true, what you initially claimed was actually true.